It is common to use a pixelated image sensor to capture the spatial distribution of light in a scene. At times, however, this is overkill. In this paper, we present a technique for 3D scanning using a souped-up photodiode. Consider a simple point scanning setup. On the left, a laser on a 2D galvo illuminates the scene and scans with a spot. An image sensor observes and reports the location of the spot, which can be used to triangulate and estimate the 3D shape of the object. The spatial distribution of light in this scene is invariably simple, which makes the 2D pixel array quite unnecessary. Now consider a setup where we replace the pixelated image sensor with a single position sensing diode. A position sensing diode calculates the centroid of the light incident on it, and when the scene intensity is simple, as is the case here, the centroid suffices to establish projector camera correspondences and obtain 3D scans of the scene. Here we show a 3D scan of a David bust on the left and a wax candle on the right. However, this idea fails for scenes with strong global illumination. To illustrate this, consider the V-groove on the left. When illuminated with a laser, the directly illuminated spot appears at one location, but there are strong interreflections across the groove. These interreflections systematically bias the centroid measurements, causing the estimated shape to be grossly inaccurate. To solve this, we propose a novel imaging architecture. We optically co-locate a spatial light modulator with the position sensing diode. We do this using the architecture here by placing the SLM on the image plane of the lens and using an image relay to co-locate it with the position sensing diode. A helper camera is also co-located with the SLM for focusing and calibration. Here's a photo of our lab prototype highlighting the main components. To suppress the effects of global illumination, we repeatedly scan the scene while showing high-frequency patterns on the SLM. For each SLM pattern, we collect intensity and centroid measurements using the position sensing diode, which we can visualize as dual images in the projector's view. Here are some typical patterns that we use on the V-groove scene. We develop a variant of the direct global separation technique of Nair and others specialized to our setup. This allows us to significantly improve the quality of the estimated shape in the presence of global illumination. And our method produces surfaces significantly closer to the ground truth scan obtained using a helper camera. Here, similar to the V-groove, the shape of a concave bowl is correctly estimated using our technique. The results in this work suggest that for many vision tasks, coarse spatial statistics suffice. Thus, unconventional sensors can provide a different set of trade-offs than traditional pixel arrays. Given this, we hope that this work renews interest in position sensing diodes and other non-traditional sensors in the computational imaging community. Thank you.